Okay. All right. So section 3, we're going to talk about dot products and vector projections. Okay. So, so suppose you have two vectors, a vector A and a vector B, and they're, joined at their initial points right here. Okay. So there are many ways to think about this. Suppose you take a flashlight, right, and hold it like perpendicular to B, right? This vector A will cast a shadow on vector B, right? If you hold the flashlight like this. And that shadow will have a certain length, right? In math, we call that the projection of A onto B. Another way to think about it more mathematically is we know now that if you have any old vector, you can break it down into its components, right? So these happen to be the horizontal and the vertical components of this, but those are not the only components that make up that vector. It could also be, let's say, that one and that one, right? These two are the components that add to that vector. Yes? So now, if I have this vector A, this blue vector A, and if I wanted to break it down into its components, right? One of the components lies along B, and the other component is this one here, okay? Then this red one is the projection of vector A onto vector B, okay? Now, I can very easily take a ruler, measure that red vector, which is the projection of A onto B, and I get a length, a scalar, a number, right? Like 3.2 centimeters. And I can also take a ruler and now measure the length of angle B, and that's another scalar, a regular old number. So now I have two numbers, the length of the red, the length of the green. When I multiply those together, I get what is called the dot product. Okay? Yeah. Okay. So, so this dot product that we're talking about is, so remember how we said this was the projection? It's the length of the projection. Okay, look at how we write the projection of A onto B. So I'll write it over here. This red here is the projection of A onto B. That's how we write it. Okay, so it's the projection of A onto B. So now if I take that length, the projection of A onto B, and if I multiply it by the length of vector B, that's the dot product. Okay, so the dot product will be just a regular old scalar, and that's the concept of what it is. All right, why do we even need to multiply such seemingly random numbers? Well, that we'll see in a little bit. Okay, so now we're not going around carrying a ruler with us. So how is it that we can find this? There's actually like the cutest little formula, and it's this. The dot product, first of all, is written as A dot B. That's literally how we write it, A dot B. And that's what we call it, A dot B. Okay, what is the formula for this wonderful little A dot B? It's A1B1 plus A2B2. Very straightforward. So take a look here. I have U and V, vector U, vector V. I want to find U dot V. So basically, this is A1B1, A2B2. So I say A1 times what?
Oh, wait, 4. Negative 3 and 4.
Oh my God, hang on. Sorry. Oh my God, sorry. I wrote these wrong. Oh my God, Miss Malikian. Sorry. I was thinking of, oh my God, I'm so sorry. This is A1, A2, B1, B2. Oh my God. I'm so sorry. So it's negative 3 times 3. plus 4 times 6, right? So that gives me negative 9 plus 24. So U dot V is just 15. Okay? Okay, questions? Okay, now orthogonal vectors. So suppose these two vectors are perpendicular to each other. Now, suppose, let's go with that flashlight again. Suppose I shine a light just like this, perpendicular to that red vector P. How much of a shadow is this going to have? None, 0, right? And remember, the dot product was the length of that shadow times this vector, where if the length of the shadow is 0, then the dot product will also be 0, right? So that tells us that if two vectors are perpendicular, but in the vector world, we don't call them perpendicular. We use the word orthogonal. Hello. Hi. Hi. So, okay, so when you, okay, what does your orthodontist do?
Look at my teeth.
I mean, yes, but that's not all they do, I'm assuming.
Why?
Why? Make them what? Straight, right? Make them straight. So like, or right? Your orthodontist does that, and like your orthopedist, like make sure your bones are straight. So that's where the word orthogonal comes from. Get it? Orthogonal. So for example, right now I am standing orthogonal to the plane of the floor. Do you see that?
No.
Right? Yes. Okay. So orthogonal is it's a word that we use in upper level math. And so if you have, two vectors, they are orthogonal. You can have a line orthogonal to a plane and so on. All right. So if two vectors are orthogonal, A dot B equals 0. And the converse is also true. Okay, let's not be obnoxious. Come on. If A dot B is 0, we know that the vectors are orthogonal. So let's find the dot product of U and V here. So U dot V is equal to 2 times negative 14 plus 7 times 4. And that's 0. So I know that U and V are orthogonal. Okay? Cool. All right. So commutative property, right? Okay. So what if you have vector A and also vector A, right? And they're like the identical vectors, right? What is the projection of A on A? Or what is the shadow of A on A? It's the whole thing, right? So the dot product here would be the length of this projection times the length of this. So the dot product, A dot A, right, would just be the length of A times the length of A, which means A dot A would just be the magnitude of A squared, which means if I take a square root of both sides, the magnitude of A is just the square root of A dot A. So that's another way of looking at finding the magnitude of a vector, okay? You guys know how to find the magnitude of a vector. So normally, and I'm going to show you these two things, and yes, they're identical, but they're two different ways of saying the same thing. So normally, how would we find the magnitude of vector A? We would just do negative 6 squared plus 5 squared, right? And that's root 61. Now, method 2, what we are talking about here, right? The magnitude of A is formally the square root of A dot A. Okay? So what's A dot A? So if that's A, and then if I reproduce A, what's A dot A going to be? Negative 6 times negative 6 plus 5 times 5. Do you see how they're exactly the same thing? That's the point, right? So A dot A under a square root just gives you the magnitude of A. Now, When you're walking down the street and somebody comes over to you and they're like, hey, I have a vector here, can you find the magnitude? Okay, you're just going to do this. You're not going to do that, but you know that it's the same thing. Okay, you know that A dot A is the square of the magnitude. Okay, has that ever happened to you before where like you had to find them and then you were like, I don't know what you're talking about? Now, when that person comes over to you again, you're just like, I can totally find the dot product of those two vectors. Bring it on. Right? Yeah. Okay, so another thing we normally want to find is this angle theta. Okay, the angle between them. So let's talk about this for a minute. Back to lovely old trig, yay, right? If this is theta, this is, so the sine of theta is what? This over A, correct? And the cosine of theta is this over A, correct? So remember talking about projections, this is A cosine theta. Remember when we were talking about horizontal projection, right? Horizontal component and vertical component. This was A cosine theta. And then the vertical one would be what? A sine theta. We don't care about that right now, okay? So if I wanted to find A dot B, okay? We just said A dot B is the length of that projection, which is A cosine theta, times what? The magnitude of B, right? Okay. Huh? Okay, so I'll tell you, because how are we finding, how did we define dot product? It's this length times this length. Well, that length is magnitude, okay? And now here too, since we're talking about vectors, when I say A cosine theta, that's actually the magnitude of A cosine theta, right? So another way to write A dot B is magnitude of A, magnitude of B, cosine theta. Is everybody okay with how we got this? Okay, now, if I wanted to just find the angle then, if I wanted to solve for cosine theta, I divide by magnitude of A, magnitude of B. So then, down here, cosine theta is A dot B over magnitude of A, magnitude of B. Yeah.
Why did you do magnitude of A?
Okay, so what's dot product? It's this length times this length. What's another word for length? Magnitude of the vector. So magnitude of B times this length. What's this length? A cosine theta. But when I say A, it's the length of A, which is the magnitude of A. Okay? Okay. Look, when we found vector projections, right? Like on the quiz, right? When you had to do, this is the horizontal and this is the vertical. How did we label them? Didn't we say this was this and this was that, the magnitude? Right? Okay, so how did we find those lengths? If this is theta, how did we find them? It was the magnitude of this times cosine theta, right? Back from the first lesson. Here, right? We did that here. It's the magnitude times cosine theta, magnitude times cosine theta. So that's what we're doing here. Okay. All right. So here we go. Find the angle theta between these two angles, 1 comma negative, these two vectors, 1 comma negative 4, 2 comma 6. Okay. So when you have something like this, you need to find a couple of things. First, you need to find u dot v. So that's going to be 1 times 2 plus negative 4 times 6. And that's negative 22. Now, I need to find magnitude of u, which is the square root of 1 plus 16, root 17. Then I need to find the magnitude of V, which is 4 plus 36 root 40. Okay, this is an intermediate step, so I'm just going to leave it like that for the time being. Okay, so now what I need to find is cosine of theta, right? Cosine of theta is U dot V over magnitude of U, magnitude of V. That's the formula. So U dot V, negative 22, over root 17, root 40. And this is the cosine of theta. So what's theta then? It's the inverse cosine of this over the square root of 17 times 40. And that's how I plug it into my calculator, all right? There is no need, if you're going to plug all this into your calculator, there's no need to simplify these, right? Who cares? So then the final answer will be, let's see. Huh? No, the dot product is not, we're using the dot product in the inverse cosine to find the angle. How much is this? 147.5. Okay, so what exactly is it that we have found here? Let's take a look. Right? So the first vector is 1 comma 4. Whoops. The first vector is 1, oh my God, I don't want this anymore. 1 comma negative 4. So that's vector u. And then the second vector is 2 comma 6. Right? That's v. What we have found is this angle in between. That's 147.5. Right? Isn't that cool? Right? Okay. So now take a look at this. Find the angle theta between the vectors in radians. Okay. Look at how this is given to us. This is given to us as a linear combination of I and j. So here we have cosine of 7 pi over 6i, sine of 7 pi over 6j, right? When we wrote those before, so this is the first vector. Basically what this is this is the x component and this is the y component of that vector. And this is the second vector, right? This is the x component and this is the y component. Okay, so the way this looks is this. The first one, we have cosine and sine of the same angle. What's the angle? 7 pi over 6. So where is 7 pi over 6? Right here. Okay, this is vector u. All right, so this is 7 pi over 6. Look at this. The horizontal component is the cosine of 7 pi over 6. The vertical component is the sine of 7 pi over 6. And so what about the other one? What's the angle for the other one? 5 pi over 4. So where is 5 pi over 4? 1 pi over 4, 3 pi over 4, 5 pi over 4. It's down here, 5 pi over 4. So that's V, 5 pi over 4. And so now, what do I need to do here? I need to find the angles in between, right? Back in geometry, speaking of geometry, guess what you learned? You learned about the protractor postulate. Basically, it says if you want to find the angle between two angles, you just subtract the two of them. So what we have to do is, if this is 5 pi over 4, and then if this is 7 pi over 4, how do I find the angle in between? Just subtract them, right? So theta is 5 pi over 4 minus 7 pi over 6. Sorry, it's 7 pi over 6. Huh? Yeah, it's 7 pi over 6. I said 4. I misspoke. Right? So theta is pi over 12. All right? No, you take the absolute value. It's just, okay? All right, so why do we need to find a dot product? What is a dot product really? Well, again, let's talk about this. You have a vector, and it's the component of that vector along another vector, right? So take a look at this for a minute. So here's this chair, right? I'm going to push this chair in, right? There are two ways I can do this. One is I can like scooch down like this and I can just push it horizontally. But who does that? That's just silly, right? You just grab onto this and you drag. So when I push this chair, look at the force in my arms. The force in my arms is being directed at an angle down, okay? But when I push down on this, all I'm doing is pushing down. I'm not pushing horizontally, but is this chair going down into the ground, into the floor? It's not. It's going horizontally. Why is that? Because I have a force down this way, right? That's my force. That force vector can be broken down into the vertical and into the horizontal component. The vertical component of my force is being wasted here. But the horizontal component of my force is being used to drag this along the floor. Okay? Now, what is the direction that this is moving? Also horizontal. So, the magnitude of my force, the horizontal magnitude of my force, times this is the vector of the motion of the chair, right? So the horizontal magnitude of my force times the magnitude that the chair moves, the distance, that multiplied together is the work I have done in pushing the force. So in science or physics, you learn about work. Back in middle school or whatever, beginning classes, they teach you work is force times distance. Not really. Work is F dot D. That's really what it is. So in order to do work, it's the dot product of force and distance, because the force that's being applied, only the component that is in the same direction as the motion is being used in the work. Okay? So, all right. So here, a person pushes a box with a constant force of 40 newtons at a constant angle of 45. Find the work done in joules to move the box 12 meters. Okay. So there are two ways to do this. Method one is this. Work is force times distance. Okay? Which is the same as the magnitude of the force times the magnitude of this times cosine theta. Right? Look, that's what we came up with over here, right? A dot B is just magnitude, cosine theta. So what is this? Magnitude of the force? How much is that? 40. Magnitude of the distance? 12. Cosine? 45. That's 339.4. Okay, what are the units? Force is in newtons. This is in meters. It's Newton meters, which is the same as joules. Okay? All right. Method two is, okay, what is the distance vector here? 12, 0, right? It's just moving 12. What is the force vector? 40 cosine 45, 40 sine 45. That's the same as what you were doing on the quiz, right? You have a vector and a whatever. Okay, so now what's F dot D? It's this times 12 plus this times 0. Okay? So what happens here? That goes away. So look, you end up with the same thing. 40 times 12 cosine 45. Right? So you see how it's the same exact thing. So whatever, 339.4 joules. Okay? So that's a little bit of physics for you in the math. All right, so